Okay, so this is the pre-recorded lecture number 7. Corresponds to the content that will be in a live lecture on the 28th, Thursday the 28th in class. And as has been happening, we'll have, I'm going to skip over some of the examples in this recorded version, and you work through those examples live in the live lecture on the 28th. Just reminders on a few announcements. Lab 2 is, let's see, this is lab number 1 in this case, sorry. It's due by the 29th, day after tomorrow, reflective of when the live event will happen. So please get that in the way. We'll be handing out the midterm the week of February 2nd on Tuesday at the end of that lecture. That is a lecture that will cover DC motors and brush DC motors, and the exam itself will include and cover content from that lecture. So we hope you'll show up. We're going to, as we've been doing, it'll be pre-recorded, plus there'll be a live problem-solving thing in the class that day, and at the end of the lecture we'll pass out the midterm. You'll also be able to download the midterm from the coursework site sometime after that lecture. You'll write up a solution all by yourself. It's the only thing you'll do this whole quarter that we insist that you do all by yourself, and we'll talk about that a little bit more on the Tuesday we give it out. It's due Friday afternoon outside my office, and there are review sessions that will be scheduling times and places. Lab 3 will come at the end of the midterm, project the following week, and off and running. Okay, so today's topic is a family of logic chips that is kind of an extension of the last lecture, but they're generally in a category, they're called power drivers. And the reason we need them is that, you remember looking through what was in the last lecture, we had a lot of sort of standard digital devices, microprocessors, logic chips, things of that sort, that had voltages that could operate, somewhere between a volt and 5 volts, and the staggering of the logic levels and all that stuff to make sure they could talk to each other. And generally the currents that came out of the output pins of these devices were in the few milliamp range, maybe as much as 10 or 20, but generally milliamps of current is what we were talking about with these families of devices. The problem is that we actually want to use these microprocessors and the associated circuits to do interesting large-scale things, which include motors, LEDs, other kinds of actuators, transmitters, and many other things. And what we're going to find is when you start looking at all those kinds of output devices, they all need more voltage. Generally 10 to 12 is a not uncommon range of voltages. And they generally need a lot more current than we're ever going to get out of a logic device. And we're going to see examples where amps are needed to make motors turn. And the range of applications goes from spinning a little motor on the Velociraptor in the lab last week. Those were probably drawing hundreds of milliamps when they were running at full speed, all the way up to something like a Tesla, which is drawing hundreds of amps running at full speed. And you just need the capacity to manage and control very, very large currents. But you can't get those currents from the output pins of the logic devices that we've talked about so far. So we need something else. We need something else in the family. And schematically, we want to think about, you've got your microprocessor or other such things. Somewhere there's a motor that has to be controlled. We're talking about devices that are sort of in between, that take information from the microprocessor and more power from the power supply and use that to operate the motors. So we're going to be talking about this family of parts that are kind of in this intermediate role. The inputs of these devices are going to look like logic inputs because they have to receive signals from the microprocessor. But the outputs are going to be completely different. They're going to be much more beefy in terms of their capacity for delivering current. A lot of these devices are going to be structured and architected like these open collector outputs that we've already talked about a few times. So your typical comparator, but also quite a lot of our power driver chips have this sort of an architecture where if you think about what's in the box, you've got an input pin or several of them maybe, you've got a supply voltage and an output pin and a ground connection. And what's happening is this thing is the thing that's going to be turning motors on and off. And the way we're normally going to operate these things is going to be some plus V supply. There's going to be a motor, and there's going to be one side of the motor is connected to the output pin. And what's going to happen here is that when this transistor, in this case the bipolar junction transistor, is on, that will allow current to flow through that transistor to the ground. And when it's off, there will be no current. And so it's the output state of this device when it's in the output low. That's the useful state on for the motor. That's the on state. So there's going to be a little bit of a logical mirror here, if you will. We're going to be talking about the low state as the on state in many cases for these open collectors. The jargon is going to be pretty strongly along that line, and I think just from a logical perspective, we usually think of the high as the on and the low as the off when we think about a lot of other devices. Here, the low state for the output of this device is the useful state and the actual on state from the standpoint of operation of things like motors. So this will be the kind of configuration we're going to be talking about. We're also going to build circuits with CMOS, and in this case, instead of open collectors, they talk about open drain. The device that's active in this case is an FET. A little bit different in terms of the details, but the basics are pretty similar. You've got your chip. It has an output pin, it has some ground connections, and it has an input. It has power supply connections and ground connections. There's a bunch of logic stuff that receives the signal from the microprocessor, figures out what the microprocessor's, is it a high or a low, what's going on, and eventually that translates to a control voltage for this MOSFET on the back end, this power MOSFET. And again, we're going to have some plus VS and a motor, and the output of the motor is what's connected. One pin of the motor is connected to that output pin. And once again, the on state is the low of the output. That's when the current flows. And it's the current through the motor that makes it do things. One interesting thing that might be useful, I'd say we throw it in here just to make the point, but I doubt you'll need much of it. But if you have groups of open collector devices, you can sort of connect all of them together, and the way they'll operate together is as an OR. So if A or B is low, then the output goes low. So, there may be some configuration where you have one set of logic circuits that are looking at some aspect of the situation, and depending on what's going on, they'll say, all right, it's time to turn the motor on. And another set of logic circuits looking at other signals and independently making the same judgment. And you want to turn the motor on in the case that either of them detects that there's something worth doing. So you might wire them together, and that's a feature of open collectors, that they can be wired together as ORs. You can use open collectors to do level shifting. So this can be 3.3 volt logic, and this can be 12 volts here. So you can have a system that in the high state goes close to 12, and in the low state goes close to 0. And depending on the voltage you pick for the pull-up resistor, you can create a logic output that is consistent with a higher voltage logic family. And that actually is done sometimes. And if you're stuck in a lab with two different logic families and you don't have time to buy a real converter chip, this is the next best and easiest thing to do, something along these lines. And as we've talked about several times already, you need to be picking that resistor so that it works in the high and the low state. And that's math that you've heard about several times and can do by now, we hope. The thing we're always going to be doing, this is application number 3 on this list, this is the main thing for this class, for ME210. We're going to be using the outputs of open collectors with plus VS and ground to basically turn logical input information into a control voltage that can turn motors on or off. And so there's a lot of current flowing through the motor that has to go through this collector to ground. We want the output pin of this open collector device to be capable of handling a lot of current. So let's start talking about some specifics here. One of our favorite open collector power driver chips is a device called the DS3658. The front page of the datasheet has a lot of jargon on it, but it's actually kind of interesting to look at some of it because this gives you a sense of how these things are described. It has 4 output pins, so it has a quad driver. It means it can drive 4 different things, and that can be useful. It has saturated transistor outputs. That's jargon for open collector. It has one very nice feature. It says that you can tie the outputs together for increased capacity. So each output, in this case we see each output can put out up to 600 milliamps, or it can sink 600 milliamps. You can tie the 4 outputs together to get 2.4 amps. And the point I want to make here is that this is not always true with all drivers. You often have a case where inside the chip, inside the package, there's 4 different electronic elements. They each have 4 different values of the output voltage in the low state or other parameters. If you tie the outputs together and turn them all on, they won't necessarily share current equally. And the problem with that is that one of the outputs may be forced into operation above its specifications, and then bad things can happen that we've been talking about the last several weeks. If it tells you that the outputs can be tied together, it's telling you that there's been some effort on the design side to make sure that the specs for the 4 outputs on this one product are close enough together that they will share the current properly. And this is a thing that is, I would say, generally not true except when stated that it is true. So never assume that's the case. And you know, really the main news here is this is a device that has inputs that are kind of TTL compatible, so they're like logic inputs, but the outputs have a lot more capacity. We're talking, you know, hundreds of milliamps up to a few amps even. So a very powerful part. It can take a little bit of logic signal and generate a large control current signal. Pinout is a little bit complicated. It's not an op-amp or a comparator. It has its own family of stuff. It has 4 inputs to control the 4 outputs. And they're independently controllable. So you can turn one thing on while you're turning something else off. All that's possible. Turn everything on at the same time. There is an enable pin here. This is a single pin that can deactivate the entire system. So you want to be sure that that is held high. If you want to operate any of the other elements of the device, if you leave that floating or tie it to ground, then nothing will ever get turned on here. There's supply voltage, and then there's actually 4 connections to ground. The reason you need 4 ground connections is that the total amount of current flowing through this device might be as much as 2 amps of current. And it's normally the case that a single pin on a printed circuit board or in a package isn't rated to handle that much current. So they're splitting the current into 4 pieces to stay underneath the threshold specification for current handling in most packages. So what you would do in use is you tie all 4 of these together and let all 4 of those connections go to ground as a parallel high capacity bus. Now on the output side, there's 4 outputs corresponding to the 4 inputs, output A, B, C, D. And the way this is operated is you'll have a plus VS, you'll have your motor, and then you connect one side of the motor to the output A, for example, and then these grounds are connected to the ground of your circuit. And so the flow of current is from the supply voltage through the motor into the output pin and eventually out of the ground pin to the ground of your system. These are sync drivers, so when the output is in the low state, that's when there's a voltage difference across the motor, and that's when the current will flow. One last feature, there's these clamp pins. What these are used for is for the case of dealing with the inductive kick. So when you're running the motor, you have a steady current flowing through it, and then you switch the output from the low to the high, you're basically turning it off. That leads to a large change in current, a large dI by dt. And for inductors, that leads to an induced voltage that's proportional to di dt times the inductance. And particularly when you go from a steady current to no current abruptly, that di dt is a huge number. That leads to a huge voltage spike on the terminals of the motor. And what you do with this clamp diode system is you make a hard connection from the high side. Oops, I erased some stuff accidentally. You make a hardwired connection from the high side of the motor to the clamp connection. And what this makes sure happens is that the voltage at these nodes never goes outside of a breakdown voltage above or below the input voltages of the motor. So as the voltage at this terminal might start to shoot upward, or the voltage at this terminal might start to shoot upward, this is a way of guaranteeing that that voltage won't get out of hand. So this is a protection mechanism for these systems. Lots of applications. You can run independently the coils of a stepper motor. We'll see some stepper motors in a week or so that have 4 windings, for example, and this gives you independent control of the current flow through all 4 windings of the motor. You can turn on a bunch of LEDs, some at a time or all at once. You can connect the outputs together, so you could take all 4 of these outputs and tie them together, and then have a single motor plus V motor connected to that, and make sure, again, all of these are tied to ground, but operate this all the way up to 2.4 amps of current could flow through this motor in that case. So it gives you a lot of capacity, something you can use for a lot of systems. All right, so let's look at some specs. This is the data sheet for the DS3658. It has input voltages, VIH and VIL. This is telling you what the input currents and voltages will be. These numbers, 2.0 for the VIH and 0.8 for the VIL, these are TTL thresholds. So they're, as we know from the last lecture, you can drive TTL logic with CMOS. Driving TTL, that's okay, and TTL can drive it. Maybe you want to check that the voltages from the Arduino are going to drive this properly, but from what I remember, the VOH of the Arduino is 3.5 roughly, and the VOL is less than 0.4, so that will be fine. You can take the outputs of the Arduino, connect them straight to the inputs of the 3658. And then on the output side, you're able to control much larger currents. So this gives you specifications for the VOL. And so, for example, if you're up to less than or equal to 300 milliamps, the VOL is never above 0.4. And if you go all the way up to less than or equal to 600 milliamps, the VOL is never worse than 0.7, never more than 0.7. So those are specs here. You notice there's no spec for VOH. That's characteristic of an open collector type of device. The VOH is not an active state. There's no control of that voltage. That's determined by the other stuff connected to the output side. And they do give you the output leakage current of 100 microamps. That would be the IOH and IOL. Sorry, that would be the IOH that would happen in the high state. So these are the specs. If we're thinking from the standpoint of logic devices, we've got our VIH, VIL, IOH, IOL, IIH, IIL. We've got a VOL and a VO or an IOL, but no specs for the output high state. That's what we normally expect for open collectors. These numbers for the voltages in the output low state are pretty good. But one thing you want to remember here is that you've got this current flowing that goes to these connections and into these output pins. If this voltage, this VOL, is 0.7, you've got power dissipation inside this chip, inside of the 3658, which is equal to VOL times IOL. So if we've got 2.4 amps times 0.7 volts, you've got roughly 2 watts of power consumption inside of this package. And it can get hot. This leads to issues with heat sinking and other such things. One other feature of this device that's something to be sort of paying attention to that's kind of interesting is it has, let's see, just looking at the specs here. No, it doesn't. So if you run this thing too hot, it might actually fail. And this is something you need to be concerned about if you're fooling around and not keeping track of your total currents. So in the way we're going to compare a lot of these devices, we're going to look at this spec. We're going to look at these numbers for the voltage in the output low state. We want those to be low, because the lower they are, the less power we're wasting cooking the chip, and that saves more power for turning the motor. And so that's kind of the baseline comparison from one to the next is going to be how low is that output low voltage. Now, the 3658 isn't the only one. As you might imagine, there's hundreds and hundreds and hundreds of power drivers out there. All the manufacturers are in this business. A lot of them make their own flavors of things, and there's all kinds of variations. And it's basically because of the diversity of applications. Some cases you need a lot more than 600 milliamps of current. So here's a power MOSFET, the IRL 9Z34N, which is something we have in our stockroom. We've used it for a lot of things, so we like it. It's not too expensive and it has nice properties. And in particular, it can handle very, very high currents with a fairly low resistance between the drain and the source. And these are specs that are commonly discussed with respect to MOSFET power drivers. So let's talk a little bit more about the details of this guy. So this drain to source on resistance, that's the equivalent resistance from the drain, or source to drain, across the MOSFET. And so the output voltage, which is taken here, or connected, the output voltage in the low state is equal to the RDS times the current flowing through the device in its active state. And they're giving us specs here. So for a drain source or gate source voltage of 5 volts and a current of no more than 16 amps of current, they're telling us that the drain source resistance is no more than 0.046. So 0.046 times 16 amps, this is ohms. That gives us a VOL in this device. When we take that product, that's less than 0.7. So if we're thinking of comparing the IRLZ to the DS3658, this thing delivers more than 10 times more current without any more output voltage increase. So it's a very capable device, delivers a lot of current with a fairly small voltage drop across the device. And this is how we would operate the device. There'd be some logic circuitry controlling it. It has its own power supply. And this load is basically, this is our motor. So when this thing is in the on state, current flows through this device to ground. When it's in the off state, that current stops. And this VOL is basically the voltage on the low side of the motor, and it's the voltage drop across the motor that determines the performance, the speed of the motor. So this is a pretty nice device from the standpoint of its ability to handle very high currents. But it is still one of these devices that is a one-way driver. So they give you the specs for this thing in the on state, which is the only state that's useful as a driver. It can sink current. It's not a current source. So it's still in the category of things we'll call sink drivers. Now there is a complementary family of parts that are called source drivers. They just have the other kind of MOSFET or the other kind of bipolar junction transistor. And the configuration from the standpoint of connections to power and ground is inverted. And they'll have the ability that in the on state, that's a high state relative to ground. And there may be instances where that's the right configuration for the logic and devices you want to operate. I will tell you just flat out, though, that the vast majority of devices in this product category are going to be of the sync driving type. And that's just because this is the way this community started, and there's just a presumption of design for sync drivers rather than source drivers. However, there is the third category, which is both. And there are instances where you want to be able to sync current and source current for the device. And for instance, that might be a situation where you're trying to drive a motor in two directions, forwards and backwards, like was the case with the Velociraptor. So in that case, you want something that might be called a push-pull driver or a totem pole driver or a bipolar driver. And what distinguishes this from all the other things we've seen is that it has both output transistors. has one that connects the output pin to high and one that connects it to low. And you switch from a high state to a low state, just as you do with logic devices, by turning these guys on and off, or off and on, depending on whether you want the output to go high or low. So if this one is off and this one is on, that's a low state, and the current will go into the output pin. On the other hand, if you have on and off, that's a high state, and you'll have current coming out of the output pin. So this is a next layer of complexity, having all of this stuff built into the chip. It's a little more expensive. There are other implications, but if you need to simultaneously source and sync current from a single node, this is the kind of driver that you need. And this is a sort of bipolar junction transistor architecture of this. There are also CMOS FET architectures that have the same capability. And again, there's a bunch of stuff in here that's not interesting, but at the end of the day, you've got a pair of FETs, and they're alternately on and off complementary states, so that you have either a connection more or less to the supply voltage or to the ground, depending on whether you're syncing or sourcing. So one device in this family, there's many others, but one that's actually kind of useful, and one that you'll use in the lab, I actually used it in Lab 1 last week, is the 555. You used it as a sync driver for turning LEDs on and off, but it could actually be used as a sync or source driver. And what's interesting here is that it actually has fairly good capability for a logic family chip. Normally it's just used as an oscillator or a timer. And that is that it can handle currents up to 200 milliamps in either direction. That makes it kind of a crossover part from that standpoint. Has some very nice characteristics. And we'll take a look actually on the next page. Here is excerpts from the data sheet. So the output voltage in the low state is 2.5 volts. And here this voltage drop, this is the voltage difference from the output pin to the ground pin. So this really is the VOL. And the voltage drop high, that's the voltage difference between the output pin and the high pin. That's the VIL. So, and as we've been talking, so if you have 100 milliamps of current, there's going to be a voltage drop inside this device that's no more than 2.5 volts. That's kind of high for a driver, but if you're talking about tens to hundreds of milliamps, that's basically survivable from a power dissipation perspective. And so 555s are actually pretty nice for turning LEDs on and off and doing some other kind of simple functionality. But it's not much current here. Remember, our logic family devices gave you up to 10 milliamps. This guy works up to maybe 100, but often we're going to need a lot more than that. So the last device that we're really going to be using quite a bit in the class this quarter are these L293 and L298 parts that are 1 and 2 amp drivers, and they are push-pull, bidirectional, and they're often referred to as H-bridge. In that there are complementary transistors that can operate the device in the high state and the low state. These are very useful, and as I mentioned, you're going to use them in class and in the project and in other places. And so the main thing is that you can take a single output and have a motor either controlled in the on state or the off state in the normal way, or you can put a motor between two terminals and have one state go low, have the other one go high, and have current flow in one direction, and then you can invert and low, and then reverse the direction of the current. So you can make the motor spin clockwise and then counterclockwise. And this bidirectional control is really important for a lot of applications. So these family of parts are representative of a category that is something we will use a lot of this quarter and talk a lot about. And just here to look at the data sheet for this thing, it has power supply pins, it has logic inputs and outputs, there's VIH and VIL, sort of the logic voltages and logic currents on the input side. And again, these numbers are in a range of values that would be consistent with most of the CMOS and TTL families that we talk about. And so you can drive these inputs with the output pins of an Arduino or most logic devices. The currents are not very high. They're in the microamp range, so those are within reach of the output currents of most of the devices we've talked about. Remember, the Arduino can source as much as 20 milliamps of current from its output pin, so there's no real problem there. Instead of giving you VOH and VOLs and all that, it gives you a parameter called saturation voltage. And this is the voltage difference between the output pin in either the high or the low state and the supply or ground pin. So what this is saying is that if you're in the high state, the output voltage will be within 1.8 volts of the high power supply voltage. And if you're in the low state, the output voltage will be within 1.8 volts of ground. Now these are not ideal numbers. It'd be nice if they were smaller, but you're making some trade-offs here in terms of the architecture of the system and its ability to handle this bidirectional current control. So I guess the real point I'm making here is that you need to remember that if you're doing bidirectional control of a case such as what's drawn in here, when you're in, say, the state where you're driving current left to right, what we're finding is that this voltage will be within 1.8 volts of Vs, and this voltage will be within 1.8 volts of ground. But the total voltage drop, so your situation, you've got plus Vs, you've got your chip, and you've got ground, and you've got your two terminals. So there's a voltage drop from Vs to this output, and there's a voltage drop from this output to ground. You get your motor in between here. So there might be 1.8 volts here, there might be 1.8 volts here. And if you've got 1 amp times 3.6 volts, worst case voltage drop, that's 3.6 watts of power consumption, which is pretty high. So this device has some efficiency issues. And really, the way you win with this device is that you can make this supply voltage higher. The size of these voltage drops doesn't change as you go up in voltage. So for example, if V supply was 5 volts and we had 3.6 volts of voltage drop inside the chip, that only leaves 1.4 volts for the motor. And we're wasting a lot of power cooking the chip instead of turning the motor. If you take your supply voltage up to 15, you've got 3.6 volts of drop inside the chip, and there's still 11.4 volts in the motor. So in that case, you're using about 90% of the power in the motor and only about 15 or so % in heating the chip. So this device is going to favor applications where the supply voltage is a fair bit above 5 volts, just because of the size of the voltage drops associated with the output saturation configuration of the device. That said, it's a very useful, very reasonable device. We're going to use it a lot. You're likely to use it in the project, and it's likely to be something you'll use in other applications later on where you're interested in control and sort of simplicity, and power consumption and power efficiency isn't absolutely your highest priority. So that would be the case in a lot of your applications. All right, so to sum up here, we've talked about a few families of devices for controlling lots of power: the 3658, the 555, the power MOSFET, and these L293 H-bridge drivers. As we go through them one by one, there's kind of a staggering of the ability to handle current, the ability to control direction, and there's a combination of features spread across this family of parts. As you're looking at a particular application, you usually start off with, what are the current voltage requirements for the thing you're operating? If it's a motor, how much current does it take to make it spin at the speed you want it to spin at, or with the torque that you need for your application? Then you go looking for power drivers that can supply that much current and have other characteristics from the standpoint of input and output voltages that are consistent with the application. You'll find there's a large variety of these parts. And what happens next, which is designing the elements and making sure they're compatible with the power driving capabilities of the chip. Here's a bunch of example calculations, and we'll work through those in the live lecture on Thursday the 28th. So please come to that. There's 5 or 6 good examples that we'll go through in class that day that'll help you sort of work out how to take numbers from the data sheets and calculate parameters from the standpoint of what will work and what won't work. So I hope this was useful. Hopefully you'll come to that lecture, and all of this will add up to good understanding of what's going on. So we'll see you on Thursday.